Here we are going to see how to do modal analysis of an electric machine. So for this example, I have chosen the Alternate 4-phase 8x6 SRM. As you can see that we have that this machine has 8 teeth on the stator and 6 teeth on the rotor. If we look at each and every component of the machine, we can see all the required elements for electromagnetic simulation of this machine. There is a stator, rotor, the motion band, the windings, and the conduction sheets. Each and everything are present here. So this is the 3D model of the machine that we are going to simulate in this example. We are going to do the model simulation of this machine. So to do the model simulation, you have to first make the 3D model. It's better not to do it in using the 2D model. The 3D model will give the more accurate result. So we have already made a 3D model beforehand, and we are going to do the model analysis of the machine on its 3D model. So I close this program, and I have to launch the ANSYS workbench from here. So I search for workbench from here, and I launch ANSYS workbench. It takes some time to launch this program. Okay, now that the program has launched, we can import the 3D model that I have shown in the previous window. Now we have to make sure that the workbench and ANSYS electronics desktop, these two softwares are coupled. If they are coupled, then only this Maxwell 2D and Maxwell 3D options will come up here, and then only we can import the .aedt file format. If they are not coupled, by default they are not coupled, so in that case the 3D geometry is to be made using ANSYS base claim. So I click on import here, then this is a this is the 3D file, the project one. You can see the .aedt file format and open it. So now it is importing. We can see the busy prompt coming up here in the left hand side bottom corner. So it has imported. We can see that the geometry is green ticked. That is, it is okay. Now we will go for modal analysis. To do the modal analysis, we have to drag and drop this modal toolbox from the left hand side panel. So we pull it and drop it here. So, and I rename it as modal stator. So we are going to do more as a stator only. Maybe we can drag and drop another modal toolbox and do for the rotor. So it's a good idea to that at this stage we save the project, because if we do not save the project, all the simulation results and the files created during the simulation will be stored in the C drive, and that might eat up the C drive space and might make the whole system slow. So it's better to save the project at this step. I write it as model, the WBPJ format, workbench project. So it is now saving. As you can see that there are so many data, so much data to save. Okay, now since the same geometry we are using, so actually we are importing the geometry from the Maxwell 3D to the model. So we have to drag and drop the geometry element here. So it is now connected. We can see the geometry element is now connected. We right click on geometry, then go to update and click on update. Means it is now actually importing the geometry. When it is done, we will see that there is a green tick beside geometry. This geometry is valid. Now we can go for the model setup. So to do this, we have to right click on the model element and then click on edit. It will open up another Maxwell toolbox called mechanical. We can see it is written here, starting mechanical, the left hand bottom corner. It takes some time to launch mechanical. Now that mechanical has launched, here we can see there is a small question mark here in the beside geometry, which actually means the geometry is not quite valid. That is because there are many sheets present in this geometry which are required for electromagnetic simulation. But since we are going to require the stator only for the model simulation of the stator, we have to right click on stator and then suppress all other bodies. It is not hide all other bodies because that will only hide but won't suppress the effect. We have to suppress all other bodies. So all the other bodies are now gone. They are crossed here. Only the stator is ticked and the geometry is now valid. Now we have to go for the mesh. We have to generate mesh on this body. Now what I do is I go for adaptive. I vary the sizing. In the sizing section, I go for the adaptive meshing and I set a resolution of 6. That gives a reasonably good simulation result at reasonably good time and computation effort. Now I right click on mesh and generate mesh. Once it is done, we can see the meshing on the body. Now we can see the mesh generated. You can see the wireframe type mesh here. Now one more setup is to be done, that is the fixed support. One fixed support is to be provided for this mechanical simulation. Now since we are not going for the whole machine body, it is quite, though not exactly accurate but quite reasonable, to apply the outer surface of the outer cylindrical surface as a fixed support. Now on the top side, on the top panel, we can see that there are options to select various geometrical elements. You can select one vertex, you can select one edge, you can select one face, or you can select one solid body. Now since we are selecting fixed support, it is valid, it is justified to take the surface, so we are selecting the surface. If someone want to select more than one surface, all you need to do is to uh, click the control from the keyboard and then keep on clicking the surfaces that we want to select and then click apply. Now since we are going for only one surface here, so I click on the outer surface only and click apply, so the color changes. Now it is the fixed support. We can see the index here, fixed support. So now all the mechanical setup for this simulation are complete. Now we can go for solution. We right click on modal and click solve and the solution starts. The solution is complete. We can see the green ticks here. So now the solution is complete. So what we can do, what we need to do here is that we have to right click on solution and insert the various, you see that the mechanical solution is complete. Now we can now see various mechanical aspects of the solution. We can see the deformation, strain, stress. But for modal analysis, since we are going to see the mode shape, the deformation is most important here. So we are going to see the total deformation. One total deformation option is created here, but the solution is not complete for this case. For this total deformation, we can see the yellow flash symbol here, so we have to solve it again. Right click on it and click evaluate all results. Since all the mechanical simulation is already complete, it the solution now occurs very quickly. Then we have to see various model frequencies and their corresponding mode shapes. Now this can be done or can be changed beforehand, before the solution is started. There is a maximum modes to find. Under the analysis settings section, the maximum modes to find is 6. Now one can increase, by default it is 6. One can increase or decrease this value, but the first six modal frequencies are the major ones, so we can, it is by default 6 and we need not change it. But you can change it, you can go for any value. Since it is an infinite body, if you keep on going for 50, 100, it will keep on showing some frequency values. So now the total deformation is available and we want to see the modal frequencies and modal shapes for various modes. For the first 6 modes, we right click on it and we go to create results at all sets. A folder, a set is created whose solution is again remaining. So we have to solve the total deformation again, evaluate all results. Now all the results are available under the total deformation. We can see it is written as total deformation 2 here. That is only to make it different from the previous total deformation. But this, if we click on this total deformation 2, we will see that it is written here mode 1. That is the total deformation 2 actually corresponds to mode 1, and the picture that we can see here is the mode shape corresponding to mode 1, and the frequency, the modal frequency corresponding to mode 1 can be seen here, 9790.9 hertz. That can be seen here. So this is the frequency corresponding to mode 1, and the mode shape corresponding to mode 1. We can similarly go to mode 2. Mode 2 here we can see this is mode 2 frequency, modal frequency, and the mode shape that has changed. Similarly 6 mode shape, this is the mode shape corresponding to mode 7, sorry, mode 6. And what's mode 6, we can see here it is written, and there is a frequency, modal frequency for mode 6, which is 9818.5 hertz. The deformation that is shown here, that is 2 meters approximately, more than 2 meter, that is not actually an exaggerated value, that is a true value. But the thing is, in the modal frequency we are actually mostly uh, concentrating on the, we are concerned about the modal frequency. It actually shows how much deformation will the body experience if we apply a very large, about Newton 10 kilonewton, in the range of kilonewton, very large sinusoidal force of this much frequency is applied on the body, then how much deformation will be there. This is the mode shape, and this is the frequency. So the frequency is important, most important here, and the mode shapes can also be taken. That is, if there is a very small frequency of this much, very small force of this much frequency acting on the body, a deformation of very small magnitude will occur, but the machine or the body will resonate at this frequency. That is the important thing here. So if you want to take a snapshot, you can simply right click on it, click the image to clipboard, then go to paint, paste here, you get the snapshot. Not saving it. Okay, so now that is done, we close the program, we save it. It is again getting saved to the F drive where I did it. Now we can see that all the components in the modal toolbox are now green tick. That is, everything is done. The setup is complete, solution is complete, and the results are available. That is all. Now similarly, I can drop another modal toolbox here. Then then I again drag and drop the geometry here, update it, and again do it for the rotor. The similar thing. Nothing changes.